Hello students, this video is the Chapter 7 multiple choice review. I'm going to be going over the multiple choice questions from Chapter 7, which is on sampling distributions. You know that a sampling distribution comes from when you take a population and then you take many different samples from that population, and from all of those different samples you collect a statistic, right? In this case, in this diagram case, it's X bar. And the next thing you do is take all of those sample statistics and put them into a distribution. And that distribution should have these two characteristics. It should be a normal distribution, and its mean should be around the population mean. Or if it's a true sampling distribution, if it's all samples of a particular sample size, then that mean is going to be equal to the population mean. Great. First, let's take a look at some of the answers, or rather all of the answers. And you'll notice in this multiple choice review, I do not have one that says skip LOL. Luckily, all of these questions are able to be answered. Let's take a look at the questions one by one. I'm going to try to go through them as fast as I can. All right, a newspaper poll. Keep in mind, a poll is when you ask certain respondents. You don't ask the entire population. Reports that 73% of respondents, you could say, of a sample, liked business tycoon Richard Branson. You know, Richard Branson is the president of Virgin Airlines. I should say Virgin Atlantic. And there he is. Look at him. The number 73% is, well, we know that 73% is not the population, because the population is people who were giving their opinions on, or who had opinions on Richard Branson, right? The population is the people that you'd be asking. So 73% isn't the people that you're asking. Similarly, the sample isn't 73% because the sample is the people who responded to the newspaper poll. It's not the 73% number. 73% is a value that is representative of that sample. So it's not a parameter. Keep in mind, parameter is a value that represents the entire population. 73% is a number that represents some value of the sample. That is otherwise known as a statistic. Whether it's an unbiased estimator or not, we're not quite sure, but we do know that it is a statistic. All right, moving on to question number 2. The name of the pattern of values that a statistic takes. Okay, well, a statistic takes when we sample repeatedly from the same population. This is kind of like what we were talking about before. When we have a statistic, which is a value that represents a sample, and then we sample repeatedly from the same population, that means we're taking one, let's say for argument's sake, X bar, we're taking one sample and finding its mean, and then we get another X bar, and then another X bar, and then we're trying to figure out, of all of those X bars, what shape or what pattern it takes, the name for the pattern of values that it takes. That sounds to me like it's a sampling distribution of a statistic. It's not population distribution because we're not dealing with individual values from every single individual. It's not a distribution of sample data because sample data is all of the individuals within a sample. We're not talking about individuals within a sample. We're talking about statistics, which is a summary value for a sample. So that's not it either. All right, moving on to question number 3. If we take a simple random sample, an SRS, as we like to call it in stat, of size n equals 500 from a population of size 5 million. Wow, 5 million. The variability of our estimate. Okay, variability, you know, is a value that is tied to a formula that is on your formula sheet. The variability of the estimate, right? The variability of, let's say, the sample statistic, let's say for argument's sake, it's X bar, is equal to, well, I know it's equal to the variability of the entire population, or the standard deviation of the entire population, divided by the square root of n. And remember, n is a specific value, lowercase n in this case. I know it looks like an H, but bear with me because I'm drawing with my mouse. Anyway, lowercase n represents the sample size, right? Sample size. We're not talking about uppercase n or capital N because that is the population size. Nobody is doubting that the size of the population from 5 million to 50 million is increasing. However, nowhere in this formula does it refer to the population size. The variability of a sampling distribution is based on the variability of the population and the sample size. Does not matter what the population size is. So much less, slightly less, no, there's no effect. Slightly greater, much greater, no, there's no effect. The answer is C. It's about the same as the variability of a sample size of n equals 500, because keep in mind, n equals 500 is the same number for both this sample, for the sample from this population and the sample from this population. Same sample size, same variability, approximately, right? All right, increasing the sample size of opinion poll. seems to me that increasing the sample size of an opinion poll, that is tied to the formula that we just wrote down up here, which is related to the sampling distribution's standard deviation. So when it talks about increasing the sample size, that means that n value is going to go up. When we increase the value of a denominator of a fraction, that means the value of the fraction overall goes down. So this variability of the statistic, the variability of the sampling distribution, I should say, is going to go down. So reduce, well, a couple of things talk about reduces here. In fact, all of them talk about reducing. Let's see what exactly goes up and what exactly goes down. Reducing the bias of the poll result, we can't say that bias is affected by increase or decrease of sample size. That's not it. The bias of a poll result is talking about whether it's consistently overvalued or consistently undervalued. That's not going to be necessarily affected by increasing the sample size. We're just going to be collecting more of a statistic that is biased. Reducing the effect of non-response in the poll, we could ask 10 people or 100 people or 1,000 people. Asking more people isn't going to reduce the effect of non-response. The effect of non-response is people that are more likely to not respond will not respond. And that's not going to change whether I ask more people or not. It's going to certainly increase the sample size, but it's not going to reduce the effect of non-response. Reducing the variability of opinions, listen, if you live in the world, you know that people have very different opinions on all sorts of different things. Reducing the variability of opinions is not what's going to happen when you ask more people. When you ask more people, you're going to get more diverse opinions. That should make perfect sense to you. And we can eliminate all of the above because we've eliminated, well, basically everything else except for B. Reducing the variability of the poll results. Remember, variability is measured by this statistic, right? This is the sampling distribution's standard deviation. That's the variability of the poll result, and that is going to be reduced when we increase n. All right, for questions 5 through 8, we're going to be talking about the magazine Sports Illustrated, which if you are a student in my class, you probably are unfamiliar with this term magazine. It's an old style book with glossy pages with lots of pictures. Sports Illustrated asks a random sample of 750 Division I college athletes. This number is the sample size. That's n. And asks this question, and then 30% of all Division I athletes. Now, this 30% is not for the sample. This 30% is for the population. This value is P. It's the parameter. All Division I athletes. Not the random sample of 750. This is all of them. Careful reading is necessary. So P hat is the sample proportion. In other words, in this 750 person sample, the value for how many of them think that performance enhancing drugs are a problem, let's say it's maybe 25% or maybe 40%. Whatever the case may be, that number is probably going to be pretty close to 30, but it's not necessarily going to be exactly 30%. So the sampling distribution of P hat, we know that sampling distributions have a very set definition for mean. That is on your formula sheet. And just in case you didn't believe me, here in section 3 on the formula sheet, here's the sampling distributions section. This is talking about the sampling distribution's standard deviation and the sampling distribution's mean. And you can see here that the mean of the sampling distribution of the sample proportions is equal to P, which is the population proportion. So if I know P, the population proportion, that should be equal to the mean of the sampling distribution of P hat. Okay, well, we know that value. That's 30%, otherwise known as 0.30. There we go. Not a problem. Next question is rudely covered up by this formula sheet, so let me shift it over. All right, the standard deviation of the sampling distribution. Now we're talking about the standard deviation. That's this value here. Well, it looks like we have a formula to figure out. It's P times 1 minus P divided by N, so it's a fairly straightforward formula to plug into the calculator. And here it is. I have 0.3, which is our P value. I shouldn't say p-value, I should say the value of the parameter p. And then 0.7, which is 1 minus p. That's, obviously 1 minus 0.3. Divided by 750, that's our n value, our sample size. So I get 0.0167. None of these answers are exactly that, but 0.0167 rounds to 0.017. There we go. For question number 7, it says decreasing the sample size from 750 to 375 would do what? Well, let's see. Let's actually do it. I put the same values into my calculator, except changing the 750 to 375, and we can see that it went from 0.0167 to 0.023. Now, this question is asking what it would multiply the standard deviation by. All right, so we're starting from 0.0167, and we're trying to figure out what would multiply the standard deviation by in order to get 0.023. So right off the bat, we can see that we went from 0.0167 to 0.023. Looks like we increased in value. So if we increased in value, we're multiplying by a number that's greater than 1, not less than 1. So we can cancel that one, and we can also cancel this one. Both of these numbers are less than 1. Looks like we're increasing the value, like I said, so we're definitely multiplying by something. And 0.0167 times 2 is not going to give us 0.023 because this number, let's say 0.017, that would turn into 0.034. That's not that. So it's definitely not 2. So it's either B or D. Let's actually multiply by square root of 2 and see what we get. And once we do that, 0.0167 times square root of 2, we get 0.2361, which is extremely close to this. So there's our answer. Why does that make sense? Well, I'll show you. The two different quantities we're talking about here is the 0.3 times 0.7 divided by 750 square rooted versus the 0.3 times 0.7 divided by 375 square rooted. You can notice that the numerators here are exactly the same. The only difference is in the denominator, and we can see that the denominator is different by 2, right? 750 is twice as big as 375. So if the question is, what are we supposed to be multiplying by? We multiply by some kind of value here. We'll call it x, right? That's going to be giving us the same thing, except the denominator is going to be half as big. That means we're going to have to try to eliminate a 2 from this denominator. In other words, I'm going to be multiplying by 2. But since this entire expression is encased inside of a square root, that means I'm going to have to multiply by the square root of 2. How about that? And that is my value of x. All right, moving on to the next question, which is also referring to this Division I athletes college situation. All right, question 8 talks about the sampling distribution of p hat is approximately normal because, well, we could answer this question sort of without referring back to the initial situation, because anytime we're asked about whether a sampling distribution of p hat is approximately normal, that has a very specific indicator, right? You can tell if a sampling distribution is approximately normal for a proportion if it satisfies the large counts condition. And the large counts condition says that if we multiply the sample size by the population proportion, and we multiply the sample size by 1 minus the population proportion, both of those things should be greater than or equal to 10. I put greater than here because there's some limitations in this computer drawing program, but suffice it to say, those different values should always be greater than or equal to 10. So looking at all of these answer choices, only one of those addresses that specific situation. The large counts condition is the thing that tells us we can assume that the sampling distribution of a sample proportion is going to be approximately normal. All of these other things are good for statistics, right? Like having a large enough sample size, whether it's a random sample, but those things don't prove to us that it's going to be approximately normal. This condition, one of the two conditions that we've tested so far, this condition indicates to us that we have a normal enough distribution. Of course, we also have to make sure that the samples are big enough, but not too big, that they're more than 10% of the population. But the large counts condition is the thing that says to us we're dealing with a normal distribution. Taking a look at exercises 9 and 10, they talk about the mathematics part of the SAT exam. They're roughly normal with mean 515 and standard deviation of 114. All right, and it also tells us that you're choosing a simple random sample of 100 students. That is our sample size, that's our N. And we're averaging their SAT math scores, and we're doing that many, many times. That is the key. When we sample and do it many, many times, and we're collecting a statistic from each sample, that's a sampling distribution. So the mean of the average scores that I get, so the mean of this sampling distribution of the sample means should be equal to the population mean. This is obviously a very terrible picture of a normal distribution, but that mean of the sampling distribution of sample means should be equal to the population mean. And we know the population mean is 515. Boom. The standard deviation can be calculated very easily. I sometimes refer back to this this reference sheet. I'll show you the reference sheet that I'm talking about here. And this is from the same page as the previous thing that I pasted in about sampling distributions. We're looking at a sampling distribution of a sample mean. So we know that the mean of a sampling distribution of sample means is equal to the population mean. And we also know that the standard deviation of the sampling distribution of sample means is equal to the standard deviation of the population divided by the square root of n. So that's an easy formula that we can put into our calculator. We are, of course, talking about this formula here, which is the standard deviation formula. We have the standard deviation of the population, which is 114. We have n, the sample size, which is 100. So we plug it into our calculator and we get 11.4. There is our answer. Where are we at here? Here it is. Now let's move on to the next question, question 11, in which it talks about newborn babies having extremely low birth rates if they weigh less than 1,000 grams. They took a random sample of 219 children. There's our N. 219 is equal to N. And they said the mean weight at birth was X equals 810 grams. This is really X bar, right? That is a sample mean that is approximating this extremely low birth weight. The sample mean is an unbiased estimator of the mean weight. Remember what unbiased estimator means. So you know from the summer assignment, I do like the website StatTrek, not Star Trek, but StatTrek. And StatTrek tells us that the definition of an unbiased estimate is when the mean of the sampling distribution of a statistic is equal to the population parameter. That statistic is said to be an unbiased estimate of the parameter. So all we have to do is figure out which one of these answers corresponds to this definition. Now, the tricky thing in statistics is that sometimes in a multiple choice question, they'll give you answers that are correct, but they don't answer the question. Remember, RTQ, ATQ, read the question, answer the question. So one of the things that's correct is, as we take larger and larger samples from this population, X bar will get closer and closer to mu. I guess like the mean of X bars will get closer and closer to mu, but that's not what this is saying. Remember, an unbiased estimator is that the mean of the sampling distribution is equal to the population parameter. That's not what this is exactly saying. Also, in all possible samples of size 219 from the population, the values of X bar will have a distribution that's close to normal. That's not what this is saying either. Remember, it's close to normal if it meets the certain criteria. In this case, we're doing a sampling distribution of sample means. We need the sample size to be greater than or equal to 30. The sample size is greater than or equal to 30, but that's not what an unbiased estimator is, right? This is a true statement, but it's not answering the question, what is an unbiased estimator? And for letter E, it says the person measuring the children's weights does so without any systematic error. We don't know that. And we're not, that isn't approached by the definition of unbiased estimator. The definition says the mean of the sampling distribution of a statistic is equal to the population parameter. We don't know the population parameter. This 1,000 is just saying extremely low birth weight is less than 1,000 grams. We don't know anything about the actual population parameter. It doesn't tell us here. It only tells us the sample mean. So we're saying that in all possible samples, the mean of the values of X bar are going to equal mu. We don't know what mu is, but we know they're going to be equal to that. That's the definition of an unbiased estimator, where the mean of the sampling distribution of a statistic, in other words, in all possible samples of size 219 from the population, the mean of the values of X, is equals a population parameter, mu. There's our answer, choice B. This is a very sticky subject, so make sure that you read everything that you can about it. For number 12, the number of hours a light bulb burns before failing varies from bulb to bulb, which makes sense. The distribution of burnout times is strongly skewed to the right. Here's my bad drawing of a skew to the right. Remember, skew right means tail right. The central limit theorem says, well, remember what the central limit theorem says, and again, I'll borrow from StatTrek. So here's our definition from StatTrek, which tells us the central limit theorem states that the sampling distribution of the mean of any independent random variable will be normal or nearly normal if we collect enough samples, or I'm sorry, if the sample size is large enough. So if our n value is greater than or equal to a certain value. So that's what the central limit theorem says. Again, in a multiple choice question, sometimes it'll have correct statements that don't match up to what they're asking. Read the question, answer the question. It's asking about the central limit theorem. As we look at more and more bulbs, their average burnout time gets ever closer to the mean mu for all bulbs of this type. That's true that the sampling distribution's mean is going to get closer and closer to the population mean, but that's not what the central limit theorem says. The average burnout time of a large number of bulbs has a distribution of the same shape as the population distribution. Well, that's not what the central limit theorem says at all. Remember, the central limit theorem says that the sampling distribution of the mean is going to be normal or nearly normal, not the same shape. The average burnout times has a distribution with a similar shape but not as extreme. That's nothing there says what the central limit theorem says. Remember, central limit theorem says it's going to be normal or nearly normal. Letter E says exactly normal. Ooh, that sounds like a guarantee to me. There's no guarantees in statistics. So there we go. The average burnout time of a large number of bulbs, in other words, we're taking a sampling distribution, if the sample size is large enough, a large number of bulbs, has a distribution that is close to normal. There's my central limit theorem hiding amongst the weeds. All right, moving on to question number 13. A study of voting chose 663 registered voters. This sounds like a sample to me. And from this sample, 72% that said that they had voted in the election. I guess, in order to be popular, you're going to be one of the cool kids that voted.
election records show that only 56% of registered voters, now this is all registered voters, right? This is a population value. So this 56%, this represents more like a parameter. Whereas of the 663 registered voters here, this is more like a statistic for a sample. Okay, so our p hat is equal to 0.72 and our p is equal to 0.56. So I would definitely say that they're different values, right? This p hat is a sample proportion. This p is a population proportion. So the sample proportion, that's a statistic, sample statistic. This population proportion is a parameter, population parameter. They're not both statistics. That doesn't make any sense. They're not both parameters. That doesn't make any sense. So one of them is one and one of them is the other. One of them is a sample and one of them is a population. Well, remember, the sample is 663 registered voters. The population is all registered voters. So that's not it. They're going to try to make you confused between sample and statistic. Keep in mind that this is the sample statistic. This is the population parameter. So the only one that's correct is choice C. 72% is a statistic. 56% is a parameter. Moving on to the next page, question number 14. And question 14 talks about increasing the size of its random sample. That's increasing n, right? The n value is going to increase. If we increase the size of the random sample, there's really one reason why you're trying to do that. You're trying to prevent one individual or some individual outliers from influencing or like changing your estimation, right? Changing your statistics. From 1,500 people to 4,000 people. That's a significant increase, right? So if you increase the sample size, you decrease the effect of outliers on the overall statistic. Remember, we're trying to estimate the proportion of voters who favor a new law banning smoking in public buildings, which thankfully in most places we don't have smoking in public buildings because that would be terrible. The effect of this increase is to, well, we're trying to increase the sample size to decrease the effect of outliers. So we're not trying to increase the bias. We're not trying to increase the variability. That wouldn't make any sense. And as a matter of fact, reducing the bias of the estimate, bias isn't affected by sample size. The only thing that's really affected is the variability. As you know, the variability is measured by standard deviation, and that standard deviation value, right, the standard deviation of the sample, sampling distribution of the sample proportion is equal to big square root of p times 1 minus p divided by n. Again, just like we talked about in the previous problem, if we divide by n and n becomes larger, this value is going to become smaller. We're reducing the variability of the estimate. This is the variability of the estimate, the standard deviation of the sampling distribution of sample proportions. Question 15. The simple random sample is size n equals 100. And we know that p hat is the proportion of success in the sample. P, remember, is the population parameter. We're trying to figure out which value of P would make it safe to use the normal approximation. Well, when we're trying to use the normal approximation for a sampling distribution of sample proportions, we need to check the so-called large counts condition. And remember that large counts condition is something we talked about in a previous problem. And here's a nice summary of the large counts condition that I found on the internet. It says that n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So basically, we're trying to figure out which of these p values, values of p, are going to meet that large counts condition. So we have to try to multiply all of these by 100 and see if we get a number that's greater than or equal to 10. All right, we test n times p for p is equal to 0.01, and we get 1. That's too small. That's not 10 or greater, so we can cross that one off. Similarly, we're going to do the same thing with 1/11th, and we get a number that's 9.09 repeating. That's not going to do it either. We need to be 10 or greater. So now we're going to multiply by 0.85. All right, 0.85 looks like it works, so that's going to be a good one. And then it makes sense that anything over 0.85 is also going to work. So 0.975 and 0.999. All three of these are going to work. Well, remember, we satisfied this condition. Now we need to satisfy the other condition. N times 1 minus p is greater than or equal to 10. Let's check that one out. It looks like this one still works. If I take 0.85 and I subtract it from 1, then multiply it by 100, it's still going to work. So it works for that condition as well. Now let's try it for the 0.975 and the 0.999. And you'll notice that both of these numbers do not give you numbers that are greater than or equal to 10. So no good, no good. My final answer has to be choice C. A quick way to do this, a quicker shortcut might be to say to yourself, well, which one of these numbers is definitely not going to work? And then which one of these complements of numbers, you can think of them as complements, is not going to work either, right? 0.975 is a large enough number that it's definitely going to multiply by 100 to give you something greater than 10, but it's too close to 1 to give you a 1 minus p, that's also going to give you a large enough n times 1 minus p. So it's not going to work on the second try. For question 16, let's move some of this other stuff out of the way. This is another fiddly question about the central limit theorem. Remember the central limit theorem we talked about before, and I brought it back just in case you forgot. Now let's try to find what the central limit theorem doesn't say. This is saying the central limit theorem is important because it allows us to use the normal distribution if the sample size is reasonably large, if the population is normally distributed. Let's find the ones that don't work. If the population is normally distributed, we don't care about the population being normally distributed, right? Central limit theorem says population can be whatever it wants to be. So population normally distributed, we can basically cut those off right away. We care not if the population is normally distributed because the central limit theorem says it's not necessary. And remember, in the actual definition of central limit theorem, it talks about regardless of any distribution, right? Any independent random variable is going to be normal or nearly normal if the sample size is large enough. Not if the population size is large enough, but if the sample size is large enough, right? Doesn't matter what the population size is. Question 17, the number of graduates at Johns Hopkins University is approximately 2,000. Nice work, guys and gals. And it also says that Ohio State University, OSU, the number of undergraduates is 40,000. Much larger, right? So these are, we're talking about these as populations. At first glance, we can see that Johns Hopkins University has a smaller population than Ohio State University. It says that a simple random sample of about 3%, so here's our sample size, 3%. It says that they're both 3%, and each sample is used to estimate that proportion, that p is equal to 0.80. Now, in previous problems, we talked about the population not making any difference. The only thing that we care about is the sample size, and at first blush, it does say 3% for both of them. So you might be pressured into thinking, oh, the sample size is the same for both, so the two estimates should have the same amount of sampling variability. Not so. Why not? Here's why. The simple random sample is about 3% of the undergraduates. 3% of 2,000 is going to be a lot smaller than 3% of 40,000. As a matter of fact, it looks like the sample size for Johns Hopkins University, the sample size is only 60, whereas the sample size for OSU is 1,200. So it stands to reason that the estimate from Johns Hopkins is going to have more sampling variability because Johns Hopkins, there's only 60 people in the sample, so there's going to be more sampling variability than from OSU. A researcher initially plans to take a simple random sample of size n from the population that has mean 80 and standard deviation of 20. This says if he were to double his sample size to 2n, what would happen to the standard deviation of the sampling distribution of the sample mean? Well, let's write out that formula. So here's our formula, and what I want to do is now change the original sample from n to 2n. So let's see how it changes. All right, it seems to me that if I want to go from here, which is the standard deviation of the population divided by the square root of n, to the standard deviation divided by the square root of 2n, I need to multiply by, well, the numerator doesn't have to change, so the numerator is going to just be 1, but the denominator has to have a 2 inside of a square root, so the denominator is going to be square root of 2. Easy peasy. There's a little Algebra 2 review for you. All right, moving on to question number 19. Student newspaper on a large university asks the simple random sample of 250 undergraduates, that's our n value, do you favor eliminating the carnival from the term n celebration? First of all, if you do, you're a Grinch. Second of all, 150 of the 250 are in favor. That means our our sample proportion is going to be 150 over 250. What is that, 3 over 5? That's 0.6. Suppose that 55% of all undergraduates, oh, that sounds like a population proportion or a parameter. So now the question is, if you took a very large number of simple random samples of size n equals 250, that's a big enough sample size, I think, from this population, the sampling distribution of the sample proportion p hat would be, well, we know the sampling distribution of the sample proportion is going to have a mean that is equal to the mean of the population, the mean of the sample proportions is going to be equal to p. That is a fact that's on your formula sheet, and it's a fact that you should know already. So we're looking for the ones that the mean of the sampling distribution of sample proportions is equal to p, which is 0.55. This one says 0.60, that's not it. This one says 0.60, that's not it. All right. This is a fairly large sample size, but we need to figure out whether it's going to be normal or going to be skewed. So we need to take this p, which is 0.55, and do the large counts condition check. Okay, according to large counts condition, we did n times p, and we found that that's way bigger than 10.
And then n times 1 minus p is also way bigger than 10. So we can say that this sampling distribution is going to be approximately normal. Not heavily skewed, as it says in letter E, but approximately normal. Now, exactly normal, that sounds suspiciously like a promise or a guarantee, and there's no guarantees in statistics. So exactly normal, that's not true. Approximately normal is what we're looking for question number 19. For question 20, which of the following statements about the sampling distribution of the sample mean is incorrect? Sampling distribution of the sample mean, we know a lot about that. We know the mean, we know the standard deviation. Let's check these answers. Here's the relevant section from the formula sheet. It says the standard deviation of the sampling distribution will decrease as the sample size increases. That's true because as the sample size increases, as this increases, that fraction is going to be smaller and smaller, right? So the standard deviation will decrease as sample size increases, so that's not it. We're looking for the one that's incorrect, keep in mind. The standard deviation is a measure of the variability of the sample mean among repeated samples. Well, that's basically the exact definition, right? That's what the standard deviation is measuring, the variability of the sample mean among many samples. The sample mean is an unbiased estimator of the true population mean. We know that to be a fact. It's unbiased because it's not going to be consistently high or consistently low. The sample means, all of the statistics that you collect from all the sample means, they're going to be clustered around that true population mean. So that's what that indicates. The sampling distribution shows how much, or shows how the sample mean will vary in repeated samples. That's what the sampling distribution's job is to do. Each one of the values inside of a sampling distribution is a sample mean that was collected from one sample of size n. So that's a correct answer. So it's not valid for this question. I know it's a weird phrasing. The sampling distribution shows how the sample was distributed around the sample. Around the sample mean. Sorry, bud. It's around the population mean. Wow, that required really close reading. Oops, sorry, that's not an X. That is, of course, a check. All right, moving on to question number 21. All right, for 21, this is a bit of a review of some concepts that you learned about before. We're filling 16-ounce bottles of shampoo, so the mean amount is 16.05 ounces. And the standard deviation is 0.1 ounce. Okay, so that information could easily be graphed on a normal curve. However, nothing here really says this is going to be a normal distribution. It says the mean amount, and it says the standard deviation, and we're assuming that the machine is working properly, and it says 4 bottles are randomly selected each hour, and the number of ounces in each bottle is measured. So that means the n value is equal to 4. That doesn't really strike me as meeting the condition that we need to have samples of 30 or more. So all the information that's given to us sounds like a normal distribution question, but there's nothing here that tells me that I can use normal distributions. So since there's not a large enough sample size for our sampling distribution, since nothing here says that the original population distribution is normal, I'm going to say none of the above. This is just a reinforcement to say we're only able to use calculations with normality. We're only able to use things like the empirical rule if we know that the distribution at hand is normal. Since nothing here says that it's going to be normal, none of the indications are correct, we're not going to use them. Now for question 22, suppose you're a student aide in the library and agree to be paid according to the random pay system. First of all, you're a big sucker if you do that. Each week the librarian flips a coin. If it's heads, your pay for the week is 80. If it's tails, your pay for the week is 40. So you're really hoping that they, for some reason, have a two-headed coin. You work for the library for 100 weeks. Suppose we choose a simple random sample of 2 weeks and calculate your average earnings. What's the shape of the sampling distribution? Well, it seems to me that there's 3 different outcomes here. You could get heads, in which case heads is going to be $160, right? 2 weeks. You could get tails, or tails. In both of those cases, you're going to get 80 plus 40. That's 120. Or you could get tails. You could be a big sucker and a big loser, and you get only $80 for the week. Here's a probability distribution that keeps in mind that we are talking about average earnings, so I should have divided all those numbers by 2, right? 160 for the 2 weeks divided by 2 is 80, 120 divided by 2 is 60, etc. And you can see that it is, there's about a 1 in 2 chance that you get $60 per week as an average. There's a 1 in 4 chance that you get $80, and there's a 1 in 4 chance that you get $40. That sounds to me like the distribution is going to have 3 different possible values. It's got 40, 60, and 80. So if we graph the distribution, it would look like this. Now, this discrete probability distribution has 2 different values that it could be, right? 0.25 is the probability for $40 a week. 0.25 is also the probability for $80 a week, and 0.5 is the probability for $60 a week. This looks pretty symmetrical to me.
However, it doesn't seem normal to me. It's not normal because it's not a continuous probability distribution. There's no chance, for example, that the person earns $50 or $66. It's either 40, 60, or 80. Also, there's no tails out here. It doesn't really follow any of the other rules for normality. So it is symmetric. However, it's not normal. Perfect. All right, unfortunately for me, that's the end of the questions. But fortunately for you, we're done with our review. That was the Chapter 7 multiple choice review. Good luck studying.